Hello everybody. In this lecture we will be discussing about the circuit symbol of BJT, NPN and PNP types, and also the direction of conventional current flow and electron flow through it, and the different currents flowing through the BJT, and also the relation between them, the expression of current gains and some current expressions. So first let us draw the circuit symbol of a BJT. So this is the circuit symbol of NPN type of BJT. You know, the PNP type means if the arrowhead will be the opposite. This side is the base terminal, this is the emitter, and this is collector. So this current going inside BJT is IB, IC is the collector current, and IE going out in the opposite direction is emitter current. So this is the conventional flow of transistor currents, conventional current flow, and obviously the flow of electrons will be just the opposite. For IB it is just the opposite. This is the electron flow for IB, this is the electron flow for IE, and this is the electron flow for IC. So this is for the electrons, corresponding electrons. So electron flow marked with red. Now this is the schematic symbol. The different currents you already know, the emitter current, base current, and collector current. Now because emitter is the source, because the emitter is the source of the electrons, it has the largest current. So emitter current IE is the largest in quantity, and most of the emitter electrons flow towards the collector. You know from the basic operation of transistors, the collector current is almost as large as emitter current, almost equal, and the base current as a result will be very small as compared to the emitter current or collector current. It is often less than 1% of collector current. Now let us look at the relation. Let us get the relation by Kirchhoff's current law. You know what is Kirchhoff's current law? It is the, at a particular node, sum of incoming currents is equal to sum of all outgoing currents. So by the application of if we consider the BJT as a particular node where IB and IC are the incoming currents and IE is considered as the outgoing current, and if we apply KCL, then we can write IE is equal to IC plus IB. This is a very standout relation for a BJT. This says the emitter current is the sum of collector current and base current, and since the base current is very small, the collector current is approximately equal to the emitter current. So from here we can write IC is approximately equal to IE, and where IB is much less than the IC. Now let us get the definitions of different current gains to establish the relation between these three types of currents. So let us first define alpha. So let us see what is alpha in case of transistors. Alpha, or alternately it is called the DC current gain, or alternately called alpha DC, is equal to the ratio of collector current and emitter current. So remember this relation, it is the ratio of IC and IE, collector current and emitter current, and it is called the DC current gain of the transistor. Now, since the collector current almost equals the emitter current, so this is the definition, and IC is almost equal to IE, you know, so DC alpha is slightly less than 1 or unity, slightly less than 1. For instance, if it is a low power transistor, the value of DC alpha for low power transistor, the value of alpha DC is typically greater than 0.99, approximately greater than 0.99, and if it is a high power transistor, then alpha DC is typically greater than 0.95. There is another quantity alpha prime or alpha dash, which is known as small signal short circuit current gain. It is known as small signal short circuit current gain. We will explain in later what is actually small signal, what is meant by small signal. So alpha prime is called small signal short circuit current gain of a transistor. In common base configuration, so this is important, in CB configuration. So this is a special case, maybe we may mention that it is only for a common base configuration that alpha dash is small signal short circuit current gain for transistor. The short circuit condition implies that load resistance RL is 0. That means what is meant for short circuit current gain? That means the load that is being driven by the BJT, that is not there, that is shorted. So RL in this case, load resistance is equal to 0. This is the meaning of short circuit. And then the collector to, if this is so, if it is short circuited, that means RL equal to 0, the collector to base voltage VCB remains unaltered. The collector to base, because that means base is common, base is grounded because it is in CB configuration. So if we measure the output between collector and base, that is the collector to base voltage, it will remain unaltered because of short circuit at the output side of the BJT, though the collector current may change. This parameter alpha dash is given by the ratio, then it is also given by a ratio alpha prime, which is change in collector current to the change in emitter current when the collector to base voltage is a constant. So we can define alpha prime as del IC, that is change in collector current, by del IE, that means change in emitter current when collector to base voltage is constant. So this is the definition of short circuit current gain in CB configuration for a small signal transistor amplifier. Now obviously the del IC and del IE respectively are the changes in collector current and emitter current. Now for a good transistor, normally alpha approximately equal to alpha prime. Now this is all about alpha. Now let us define what is beta for a transistor. The DC beta, or alternately it is written as beta DC, it is defined as the ratio of DC collector current IC to the DC base current IB. So this is the basic definition of beta. So DC beta, also known as current gain, it is also a current gain which is the ratio of IC and IB, and because of small base current produces a much larger collector current, because base current will be a very small quantity with respect to the collector current IC. So that means the value of beta should be much higher, unlike alpha. The current gain is a major advantage. This parameter beta will be a major parameter for a transistor, which has led to all kinds of different applications for a BJT. For low power transistor, that means whose power handling capacity is less than 1 watt. For low power BJT, whose power handling capacity is less than 1 watt, for them this beta is typically between 100 to 300. Please remember these ranges, the value of beta. And for high power transistor, that means it is that high power transistor is that which can handle power greater than 1 watt, usually have current gains beta between 20 to 100. So these are the important values for beta. Now this beta is the maximum current gain that can be obtained with the transistor when operated in common emitter mode. So in alpha we have seen it is measured when operated in common base mode. So that is important for alpha CB configuration, but here for beta it is operated in CE configuration. So this is important. This is the difference between alpha and beta. So while the transistor is working in CE configuration, the beta is being specified, unlike alpha, which is being specified for CB configuration. Now this beta will be later on, you will see that this beta can be alternately called HFE. When we will discuss the H parameters, you will understand that HFE is such an H parameter which is nothing but this current gain beta. So the symbol, once again, beta will be giving us a parameter beta prime, like alpha gave the parameter alpha prime. It is also the small signal short circuit current gain, like the alpha prime. Small signal short circuit current gain, also designated by HFE. But beta and beta prime are something different. Beta prime is actually H small fe, but when it is beta, it should be actually written as H capital Fe. That means capital F means, I have already told you, capital means it is DC and small means it is AC. So since this beta, the beta which we have discussed, that was beta DC, that is H capital Fe. But now we are discussing about beta prime, it should be mentioned with H small fe. It is AC beta rather. It is small signal short circuit current gain in common emitter configuration. So beta prime should be defined as del IC by del IB. It is the ratio of change in collector current and change in base current at a constant collector to emitter voltage. Previously what was constant? Collector to base voltage, but since beta is being specified in common emitter configuration, that means emitter is the reference or the ground for all the voltages and currents. The input side for common emitter mode, input side is base with emitter and output side is collector with emitter. So the output voltage will be measured between collector and emitter, so it is VCE. So in for alpha prime it should be VCB constant, and for beta prime it should be VCE constant. So this is the definition of beta prime. Beta prime is H small fe del IC by del IB, keeping VCE constant. Now in normal operation, beta prime differs from beta by less than 20%. So the difference between beta and beta prime is less than 20% for normal operation of BJT, and the value of beta is already I have mentioned for low power transistor and high power transistor. So this is all about the definitions of beta, beta prime, alpha and alpha prime. Now let us find out the relation between the alpha and beta. So first, now let us see the relation, how to find the relation. It is a very important topic of study of analog electronics, relation between alpha and beta. So let us first draw the basic diagram of a transistor. This is emitter, this is collector, and this side is base. Consider it as a PNP transistor. You can see the arrowhead is from the emitter terminal going inside the transistor. IB is flowing inside this, I is flowing inside this through emitter terminal, IB is flowing through base terminal, and collector current IC is flowing through collector terminal inside the BJT. So if this is the diagram, so now if we apply Kirchhoff's current law here, we can write IE equal to minus as common IC plus IB based on the reference directions as per here, as per given here, as per shown here. So now if we use the equation mentioned with the relation of alpha, that is IC and IE, and since IC and IE are oppositely directed, so here we should write IC is equal to minus alpha IE, minus because of IE and IC are oppositely directed. Now if we substitute this equation, from this equation the value of IE into this equation, the value of IE means it is minus IC by alpha, that is being put over here. We can write, so give some equation number. This is equation 1, this is equation 2. So what we are doing now, substituting IE from equation 1, substituting IE from equation 1 into equation 2, substituting IE from 1 to 2. What we get? We obtain IC equal to minus alpha, substitute IE is minus of IC plus IB, minus of IC plus alpha, so it is alpha into IC plus IB, or we can take this alpha IC to the left side, so we can write therefore alpha IC to the left side and take IC common, so IC into 1 minus alpha, that is equal to alpha IB. So from here we can find IC by IB, or IC by IB is nothing but alpha by 1 minus alpha, and you know what is IC by IB, it is beta. So what is the relation we have found? Beta equal to alpha by 1 minus alpha, so beta equal to alpha by 1 minus alpha. So it is the relation. So this remember this and practice practice hard this relation, because it is a very important relation to solve different numericals. Now let us see next some current expressions. Those are used in problem solving of BJTs. Some important current expressions for BJT. This will be used for solving numerical problems. The collector current you know the collector to base junction is reverse biased, and you know for a reverse biased junction there is a reverse saturation or leakage current. So the actual collector current IC is composed of a component ICO called reverse saturation current. So inside IC it is having a component which is called ICO, or alternately called reverse saturation current. It is a part of IC because of reverse biased collector junction. So it is an integral part of IC. Previously, till the time we have discussed about BJT, initially we have ignored this part of current, but for mathematical purpose we need to consider all the different components. So now we will be considering this component to find different expressions for transistor currents. So the collector current equation will become IC, considering this ICO with it, equal to minus alpha IE plus ICO. Previously it was only the expression of alpha minus IC equal to minus alpha E. Now the ICO part has come. So give this equation a number 1. Now previously, by using Kirchhoff's current law at the BJT, we had written IE equal to minus IC plus IB previously. Okay, give this equation another name, it is 2. And now so using equation 6, using these two equations, we can write IC. If we combine these two equations, we can write IC is equal to we need to rearrange these two equations. That means just we will compare the IEs between these two equations to eliminate the value of IC. So rearrange the first equation, IC minus ICO, IC minus ICO divided by alpha, putting a minus outside, is equal to IE, because IC minus ICO is minus alpha IE, and if we take minus alpha to the left side, that means it will be IE. Now from rearranging the equation to IE, we have already found minus IC plus IB. Now if we compare these two equations, we may write this minus IC minus ICO by alpha is equal to minus IC plus IB. So from here we may write IC minus ICO is equal to alpha into IC plus IB. Now take alpha IC to the left side. So take to the left side, IC minus alpha IC is equal to IB plus ICO, and take IC common, 1 minus alpha equal to IB plus 1 alpha is missed, alpha IB, this is alpha IB plus ICO. So IC is nothing but alpha by 1 minus alpha into IB plus 1 by 1 minus alpha into ICO. Now from here, just a little while earlier we had found that beta is equal to, the relation between beta and alpha is beta equal to alpha by 1 minus alpha. So if we replace this alpha by 1 minus alpha with beta, so we can write we can replace this. So IC should be equal to beta IB plus beta plus 1 ICO. So this is an important current expression for BJT. Now how this 1 by 1 minus alpha is beta plus 1? You can find it from here. Just 1 minus alpha. You can consider, just add beta plus 1 and add with this side, that is alpha. Just combine this to beta minus alpha beta equal to alpha, or you can get from here beta equal to alpha plus alpha beta, or from here we can get beta is equal to alpha 1 plus beta, or alpha equal to beta by 1 plus beta. So this is an alternate relation between alpha and beta. This is beta in terms of alpha and this is alpha in terms of beta. Now these two relations can be equally used for your for solving different numerical problems. And if in this case, if you add with this beta plus 1, so this is alpha by 1 minus alpha plus 1, so you can get 1 minus alpha, alpha plus 1 minus alpha, so it is 1 by 1 minus alpha. So this is nothing but this term, so we can write instead of this beta plus 1. So this is one of the useful current expressions for BJT. Now this equation we have just found IC equal to beta IB plus beta plus 1 ICO. Instead of writing this big term beta plus 1 ICO, this whole term is replaced with a value ICEO. So modifying this, the equation will be IC equal to beta IB plus ICEO. See, this is the modified expression, current expression, where this term ICEO represents the collector current when the base is open circuited, that is when IB equal to 0. When IB equal to 0, that is the base is open circuited. So if we open circuit the base, that means if we make the input circuit open and no base current is being flown, so in that case the amount of collector current will be this ICO. That means this is absolutely the leakage current that is being flown between the collector and emitter terminal when the base is open. And in this case you have to remember the emitter terminal is grounded, it is in common emitter configuration. So the leakage current will flow from the collector terminal towards the grounded emitter terminal. And this relation IC equal to beta IB plus ICO, so this gives the actual current expression between involving the three quantities IC, beta and IB along with this term ICO, which is being considered over here. Now you need to keep remember one more thing, one important thing, that is while applying all these equations to solve numerical problems to actual transistors, proper sign corrections have to be made. And for IC, IB and IE, and the equation given by this boxed expression IC equal to beta IB plus ICO, this boxed expression remains unaffected, and the equation along with this IC equal to minus alpha IE plus ICO will become in some problems, in some numericals, to solve some numericals, it will become alpha IE plus ICQ, considering proper sign convention to eliminate this negative sign, and this ICQ will be nothing but the Q means quiescent. I will explain this term quiescent in a later part, but for the time being, quiescent means the QUIESCENT. Quiescent means the DC operating condition of the transistor, which will fix a particular parametric position of the transistor for its best operating condition. And to get the best value of collector current, that is denoted by ICQ, for proper operation of transistor, this ICO will be replaced by this ICQ. So this is all about the different current expressions used to have with the operation of BJT, and these will be required for different derivations and numericals later on.